close this window, and we can now go in here. We can select the lattice. We can go into sub-object mode. We can select these points and we can deform these around. And you can see now that the cube is now taking part in the lattice. So as you can see, the workflow in Maya varies slightly from the way it does in Max, and you can see the hypergraph plays a much larger part in setting up the way the nodes in your scene are actually joined together. Now that doesn't mean that you can't use the schematic system in 3ds Max to do the same kind of thing, and you can also use manually wiring together controllers using the wiring system or instancing controllers and so on. But hopefully this particular example is giving you an insight to the way that Maya handles proceduralism. Now let's move on now and have a look at the way a similar setup is actually handled within Houdini. Here's our Houdini scene, and everything we'll be doing will take place within the model network. So we'll go into the model network by pressing I. First thing we need to do is to actually generate a box, so we have something to deform. So hit tab and generate a box. Set its type to polygonal mesh, set its size to 211, and set its axis divisions to 8, 2, and 2. So it's only divided on the x-axis. Next up, we'll create a group SOP, which we'll come back to later, because we need to define individual groups to deform within the lattice SOP. We'll set this to points, because that's the type the lattice is expecting, and we'll call it box point zeros. And you'll see if you middle click on the object, you'll see that it has 32 points in box point 0. Next we need to make a copy object, so we'll create a copy SOP. Create 3 copies. Now we can set the offset for the translate on X manually, like so, by hitting middle mouse and using the ladder, or, and this is a neater way to do it, go back into the box object and copy the size parameter by holding the right mouse on the dialog. Then we go back to the copy SOP, and in the X dialog, right click and paste copy results refs. And you'll see it's created a little expression there that automatically sets the X translation for the size. So if we resize the box on X, you'll see that our 3 copies always remain end to end. Back to the copied object. The next thing we need to do is to define a point group for each individual object. And we can do that by stamping attributes onto each object, onto each copy rather. So we turn stamp inputs on, and we create an attribute called copy number, and set its parameter to $CY. $CY is a per object attribute that contains the number of that copy. So copy 0, for instance, will have a $CY attribute that actually contains the value 0. The thing is now that copy num can actually be evaluated further up the chain. So we go back to the group SOP, and where we have the group's name, we'll set an upnode expression using the param function. Param takes 2 arguments. The first one is the attribute that it's trying to find. So we'll give it the copy num attribute, and the second argument is the default value if it can't find it. Now what that will do is for each copy it'll look for the copy num attribute, and if it finds it, it will drop that into the box points group name. So if we now middle click on the bottom object, you'll see that we have each individual box in its own group. This will come in handy later. Next, we need to drop a lattice so that we can actually deform our objects. And the lattice, as you can see, takes 3 inputs. The first input is the geometry you want to deform, the second is the rest lattice, and the third is the deform lattice. So we input the output of the copy SOP into the input of the lattice SOP. Now if we try and turn that on, we basically get an error. It's actually looking for the 2 other lattices. So to give ourselves a lattice, the easiest way to do that is to create a bound object, which will generate a box based on the input SOP. So now that we can see our copies automatically generate